This is our video lab report for our Electromagnetic Motor Lab. We are investigating how changing the current flowing through a wire affects the speed of our electromagnetic motor. To do so, we changed the size of the battery we use to run the motor. This changed the current. We used 3 different batteries: a D cell battery, a C cell battery, and a AA cell battery.
For our experimental design, as shown in the diagram on the left of the slide, a battery and magnets were attached with a wire coiling around the magnets and then being balanced on top of the plus side of the battery. The electric field lines are then shown behind the battery and the magnets, showing how the current moves through the wire and thus completing the circuit through the magnets, and the battery. A more simplistic circuit diagram is the image on the right of the screen. We chose to change the size of the batteries D, C, and AA to change the amount of current going through each wire, and thus changing the speed of the wire. Then by recording the movement of the wire on video, we can calculate just how many spins per second the wire moves for each battery.
Here we have a system schema for our electromagnetic motor. The interactions between the charges on the wire, the battery, and the magnetic field are occurring due to the fact that we have the magnets, battery, and wire all connected in our circuit. This is our force diagram for our model. The direction of the force varies depending on where you are, so we chose a single point and drew the force diagram at that exact location. We were able to find this force using the right-hand rule.
The right-hand rule that we used to determine the direction of the magnetic field was the one that uses your thumb as the direction of the current, and your fingers will wrap around like a bar or a rod, and that will be the direction of the magnetic field. It'll be sort of circular depending on where exactly whatever it is affecting is.
We made a few different assumptions doing this lab. We assumed that we started with a fully charged battery and that it did not lose any charge throughout the course of the experiment. We also assumed that anywhere on the wire there was an equal amount of current. And lastly, we assumed that all other forces, such as gravity and air resistance, were negligible.
The data that we collected showed that as the battery size got larger, the number of spins per second increased and the current increased as well. And the current was measured in amps, and for D battery that was 1.5, for C that was 0.7, and for AA that was 0.5. And the spins per second for D was 16, for C was 10, for AA was 8. And we got the spins per second by taking a slow motion video that was 8 times slower than real life and multiplying the amount of spins in 1 second of that video by 8. The following videos clearly show that the larger batteries had a much faster spin rate than the smaller batteries did.
One source of error could be the friction between the wire and parts of the circuit. The wire may have been wrapped looser on one stack of magnets than another, thus slowing down the spin. Another could be that when it was balanced on top of the battery, it could be moving around, thus causing more friction from not being stationary in one spot. Another source of error could be the wire movement, this being like the air resistance that's enacting on the wire itself as it's moving around the battery.